Hello, Luke. Welcome to Lesson 54. So today we're going to be talking about substitution and simultaneous equations. But to begin with, let's talk a little bit about values. So going all the way back to the beginning here for a second, if we think about numbers in general, what is a number? So let's take a look at the number 4, for example. What is this? Well, it is a symbol. It's a symbol that is representative of some value. Okay, so in this case, it's representative of 4 items, something that looks like this. This many items right here. Okay. Now, there are multiple ways that we could express symbolically this many items. One way is to express it with the symbol 4. Another way might be to express it with an expression such as 3 plus 1. That would also have the value of 4. Okay, so it's still representative of this amount of items, all right, this number of items. Another way to express it might be 5 minus 1, or maybe even 2 times 2, or maybe something a little more complicated. We could go, let's see, 24 divided by 3 plus 2 minus 6. I believe that's also going to wind up being 4. Okay, so there are multiple ways that we can express value. All right, all of these are equivalent to each other. They're all expressing the same value, so they're all equivalent. They just look different. All right, so bear that in mind because that's going to be kind of the foundation for some of this work that we're going to be doing today. So we've done evaluations in the past where they've given you an expression and then they've said, evaluate this expression given that x is 2 and a is 3 and c is negative 4 or something like that. So let's take an expression such as x plus 3. We'll keep it simple. All right. Now, if I'm going to evaluate this expression, I need to know what x is. And let's say that we know that x is equal to a 4. X is equal to 4. So how would we evaluate this? Well, we would plug in a 4, right? So just to make it very clear here, we plug in an x for the, or excuse me, a 4 for the x, and then we simplify. So the 4 plus 3 is going to give us 7. Now, the thing that I want to stress here is that we plugged in the 4, but we could have plugged in any value that is the same as 4. So, for example, this expression here, we could have used 3 plus 1. It's still representative of 4, so therefore it is still equal to an x because it's equal to 4. So if I wanted to, I could plug into this first expression, x plus 3, in replacement for that x, I could plug in the expression 3 plus 1. And then the rest of the expression. And we're going to find out that that still gives us a value of 7, right? I plugged in some different numbers, but we still ended up with the value of 7. And the reason is that these other numbers have the same value as the first number that we plugged in. So in like manner, I could do that for any one of these expressions up on top. The most complicated one, of course, would be the last one. So let's just kind of show that. I could plug in this 24 over 3 plus 2 minus 6. I'll keep it the same here. And then plus 3 is going to be equal to, well, 24 divided by 3 is 8. 8 plus 2 is 10. 10 minus 6 is 4. And then 4 plus 3 is 7. So again, we see that no matter how complicated this expression is, so long as it has the same value as the original value for x, we can plug it in. All right? So that seems like it's really obvious and maybe not even worthwhile mentioning. Maybe it seems kind of trivial. But in fact, it is very, very useful. And we're going to see that in the next couple of problems here. So this process that we've been doing here, this is known as substitution. And that's what we've been doing for quite a while now when we evaluate problems. We just substitute the x. Substitute meaning we take the x out and replace it with something else. We take the x out, we replace it with the other value for x, the known value for x, and then we solve the expression, or we simplify the expression. That is what substitution is all about. We're subbing something in. All right? So now let's move on to simultaneous equations and start talking about those. All right, so here we have two equations. And to begin with, I just want to stress that these equations have infinite solutions. Right? We've learned that in the past. It's an if we take this first equation, it's an equation of two unknowns. It's a linear equation. It's a polynomial. It's made up of polynomials. And therefore, there is an infinite number of solutions to this equation. And we could show that by just remembering that, we can kind of draw our table here. And we can say, well, let's select some values and find some solutions. Let's, have our x and our y's. And let's say we plug in a 0 for x. Well, what's that going to give us for the y? And again, we're dealing with this first equation. If I plug in a 0 for x, I substitute a 0 for the x plus y equals 5. I could now solve this equation. 2 times 0 is 0. So 0 plus y is simply y. Y is going to equal 5. So one solution to this equation is going to be 0, 5. Remember, our solutions are in the form of an ordered pair because we have two unknowns. So we have a number for the x and a number for the y. That is one solution for this linear equation. But I could, find infinite solutions here. I could plug in a 1 if I wanted to and simply replace the 0 with a 1. And I have 2 times 1 is 2, so I end up with 2 plus y equals 5. I subtract the 2 from both sides, and I end up with y is equal to 3. So now we know y is equal to 3, and 1, 3 is another solution to this equation. And I could keep going on and on and on and on and on forever, finding solutions. Similarly, I could do the same thing with this second set. The second equation. I could find infinite solutions forever and ever for this second equation as well. All right? Now, if we're being told that this is a system of equations, and we are usually told that by a symbol. So if we see this symbol kind of enclosing these two equations, or you might think of it as kind of tying them together, this symbol represents that these equations are simultaneous equations. Okay? And what that means is that there may or may not be infinite solutions to this set of equations. Each individual equation has infinite solutions, but we're only interested in the solutions that are a solution for both equations. Okay? And so if you think about it, if we take this first equation, one solution was a 0, 5. All right? Now, if I substitute those values into the second equation, what's that going to give me? Well, the second equation is x is equal to 2y. I'll just rewrite it. Now, if x is a 0, I could replace the x with a 0. And the y is a 5, so I can replace the y with a 5. And that's going to give me 0 is equal to 10, which of course is not true. Okay? So therefore, 0, 5 is not a solution to the second equation. It is a solution to the first one, but not a solution to the second one. And because this is these are simultaneous equations, we are only interested in the solutions that are solutions for both of them at the same time. So 0, 5 would not be a solution for this system of equations. So again, simultaneous equations or systems of equations, they both mean the same thing. They mean two or more equations that we're enclosing in this brace, indicating that we're only interested in the solutions that solve for all of them at the same time. Okay, so 0, 5 would not work. Now I could try 1, 3. I could plug 1 and 3 into here, and that's going to give me 1 is equal to 2 times 3, which is 6. So 1 does not equal 6. 1, 3 is not a solution. And I could keep going down my manufactured list here until I finally, hopefully, find some solution set up here that is also a solution set for the second equation. Now, I could be doing that for a very, very long time. But that is the goal for these systems of equations. Another way to think about this, and you will learn this later on as well, but it's not bad to kind of have a picture of what's going on here as well. If you think about graphing these equations, if we have a graph, and we won't bother actually, plugging these in. But let's say it's, the first equation is doing something like this, I guess. So let's say that's our line for the first equation. And then for our second equation, x is equal to 2y. Well, that's going to look something like this, let's just say. So there's our second graph for our second equation. And remember what these graphs indicate. This first line indicates all of the solution, all the ordered pairs that would satisfy this first equation. The second line here is indicating all of the ordered pairs that would satisfy the second equation. So the place that we are interested in is actually this point right here. What is the ordered pair for this point? So it's some x followed by a comma and then some y. This is the question. What is this ordered pair, this dot? Because at that spot, it's a solution for both our first equation and for our second equation. So graphically, that's kind of what's going on here. All right, we're looking for that one area, that one spot that's satisfying both of these equations. And that would be a solution for both. So how would we do that? Short of actually picking multiple points forever and ever and trying them in our second one until we finally get a solution. Well, there's a much easier way to do it. And it goes back to what we talked about at the beginning of this lesson. So what we need to notice here is that this second equation is x is equal to 2y. And just like previously, we said that when x was equal to 4, well, that implied that x was also equal to 3 plus 1, equal to 5 minus 1, equal to 2 times 2, and so forth. Same thing applies here. X is equal to something. We don't know what x is equal to. It's a question. That's what we're trying to figure out, right? But we also know that x is equal to 2y. So whatever this something is, that is also going to be equal to a 2y. It's going to look maybe different, but it's going to be equal to a 2y because that's what our second equation is saying. And that has to be true. Okay? So the benefit here is we can just say, oh, well, we don't know what x is per se, but we do know that it's equal to 2y. So let's substitute in 2y. Okay? So what we're going to do is we're going to take the second equation and recognize that that's all set up for us in the form of x is equal to something. And then we're going to go back to our first equation and plug that something in. So we have in this first equation, we have a 2x. Well, actually, let me back up. We have a 2, and then we have an x. But we know that the x is equal to a 2y. So we're going to substitute in for that x a 2y. Now make sure that makes sense to you. We have an x. We know that the x is equal to 2y, so we can replace the x with a 2y. Okay? Just think about that for a second. Make sure it makes sense. All right? Now, once that's made sense in your head, we can move on. So we have a 2 times x, which is actually just 2y, and then we have a plus y equal to 5. Now, why did we do this? How does this help us? It helps us because now we have an equation in one unknown. It's just a y. The x's, they've disappeared. They've been replaced with y's. All right? And the benefit of that is that we know how to solve an equation with one variable. So we can actually simplify this and then solve it for y. So if we simplify it, we say 2 times 2y is 4y, plus y is equal to 5. 4y plus 1y is 5y is equal to 5. And look at how nicely this works out for us. We can divide both sides by 5, and we end up with y is equal to 1. All right? So now, what do we know? We know that the y is equal to a 1. So we can now go back, and we can really choose. We can either substitute 1 for all the y's in the first equation, if we want to, or we can substitute all the y's in the second equation. Either one will give us an equation with one variable, and that one variable will be the x. And then we could solve to find out what x is. Because remember, this is only half of our answer. Our answer has to be in the form of an ordered pair, with an x first and then a y second. We know what the y is now, but we don't know what the x is. Remember, we're looking for this point. So we know that it's, at the y position of 1, but we don't know where it is at the x position. All right, we still need to find that out. So let's take this y, plug it into one of these two. And since we've been working with the first equation, let's just do the second equation. We could do either, but we'll do the second. So the second is saying x is equal to 2y. Well, now we're going to replace that y with a 1. So it's going to be x is equal to 2 times a 1, which is really nice. X is therefore equal to a 2. Okay, so that is the x coordinate of our ordered pair. This then is our solution. That is the one and only spot on, within both of these solution sets where the solution is the same. Another way to say it would be it's the only coordinate, or I should say ordered pair, graphically shown here where it would satisfy both equations. All right, so it's right at y is equal to 1, x is equal to 2. And actually, my graph was pretty much right there. Okay, not bad. So it's at that point 2, 1. All right. So again, just real quick recap. We have two equations. They're enclosed with a brace, indicating that it is a system of equations. And we're only interested in the solutions that'll satisfy both equations at the same time. To algebraically come to the solution, we're going to recognize that this equation 2 is all set up for us as being written in terms of x. So x is equal to 2y. So we're just going to substitute that 2y value in for all of the x's in the first equation. That'll give us an equation that's solvable for y. And once we know y, we can plug that back in, substitute it back into one of these equations, and get our x. All right? Now, just as to make my point, we plugged that back into the second equation. What if we had plugged this y into the first equation? What if it still worked out? Well, let's just do it for the fun of it. The first equation was 2x plus y equals 5. So we're going to replace the y's with a 1, and we end up with 2x plus 1 is equal to 5. And now we can solve for x. Just a little bit more work here, but we subtract 1 from both sides, and we end up with 2x is equal to a 4. And then we divide both sides by 2, and we end up with x is equal to 2, which is exactly what we got over here. All right, so you can see it's not going to affect our outcome by choosing a different equation. Okay, so that is the detailed version of it. Let's try another problem now and just kind of go through the process. All right, so here we have a system of equations, and we're going to try to solve it by using substitution, meaning we're substituting something in for one of the variables. All right, so here again, second equation seems to be the one that's kind of nicely written out for us because it's in terms of x is equal to something. So we can take this, and we're going to plug that in to the x up here, because that's what x is equal to. So that new problem is going to become 2 times the negative 3y plus 11. Notice I'm using parentheses. Very important when we're substituting in. to use parentheses, because otherwise things will not work out properly. Notice this has to be now a distributive property because of the parentheses. So make sure you use the parentheses when you substitute values in for a variable. All right, so we have 2 times this whole quantity minus a y equals a 1. Now we can simplify and solve the equation. So again, we need to distribute this 2 through. So 2 times a negative 3y is a negative 6y. And then distribute the 2 through to the 11. 2 times 11 is plus 22. And then we have our minus y on the outside. And then we have a negative 6y and a negative y. Well, that's going to give us a negative 7y plus 22 is equal to 1. We subtract the 22 from both sides, and we end up with negative 7y is equal to negative 21. We can divide both sides by negative 7, and that'll give us y all by itself is equal to a 3. Now remember, we are not done yet. This is only half of the answer. Now we're going to take that and substitute it back in. And like we did last time, let's just substitute it back into the second equation. So the second equation would become x is equal to a negative 3 times the y, which we decided was a 3, plus 11. And there we have x is equal to a negative 9 plus 11. X is then equal to a 2. So the solution to this system of equations is 2, 3 as an ordered pair. That is the solution to this equation. And if you ever wanted to check that, just plug them in, and you should end up with true equations for both of them. So let's just do that just for the sake of thoroughness here and to show how that would work. Plugging this back in, we'd have a 2 times an x, which we now say is 2, minus a y, which we say is 3. That's supposed to be equal to a 1 based on this first equation. Is that true? Well, 2 times 2 is 4. 4 minus 3 is 1. So yes, 1 does equal 1. The second equation would look like a 2 for the x equals a negative 3 times the 3 for the y plus 11. Now, does the left side equal the right side? So this side is a 2. We have a negative 3 times a positive 3, negative 9. Negative 9 plus 11 is a 2. So yes, it does. Both of these check out. So 2, 3 is a solution for both of these. Okay? Very good. So let's move on to the next one. Why don't you pause the video, try this one on your own, and then we'll go through it together. All right, so same setup. And again, it seems to be that the second equation is the equation that we're going to use because it's already set up for us in terms of y is equal to something. All right, it's not x is equal, it's y equal this time. But that's all right. We don't care which variable we solve for first. This one is obviously the one that it's set up for. So let's plug this into the y, all right, because that's what y equals. So we have 2x plus 3 times a y, which is now an x minus 6, is equal to a negative 13. All right, multiplying this through, we have a 2x plus 3x minus 18 equals a negative 13. We can combine to get 5x. I'm also going to move this 18 over to the other side and have a plus 18 over here. All right, plus 18 and a negative 13 is going to give me a positive 5. Now I can divide out the 5 from both sides, and I end up with x is equal to 1. So that's part of our solution. Now we'll plug that back in. The easiest one would be the second one here. It's a less complicated equation, so let's just use that. So we have y is equal to an x, which we say is a 1, minus 6. So y is going to be equal to a negative 5. So my solution set is going to be, my solution ordered pair is going to be 1, negative 5. And that would be my answer. All right. Again, it's not a bad idea to check. So if I have x is a 1, that first equation is going to be 2 times 1, which is 2, plus 3 times y, which is a negative 5, so it's going to be a negative 15, equals negative 13. And a positive 2 and a negative 15 is indeed a negative 13, so that one does check. The second equation, well, the y would be a negative 5, equals the x, which is a 1, minus 6. So we end up with a negative 5 is equal to 1 minus 6, which is a negative 5. That one also checks. So we know that this indeed is a solution to both equations. All right, we've got a couple more here. So why don't you pause the video, try both of these, see how you do, and then we'll do it together. All right, so let's give these ones a shot. Pretty straightforward. There's nothing tricky about these. They're the same thing that we've been doing all along. It's even the second equation again, which doesn't always have to be the second equation. Sometimes it might be the first equation that would make the most sense to try to use for substitution. But in this case, it's pretty much all the second. And I actually, by the way, I took these problems directly from your book. So these are the same ones that they show in their lesson. All right, so plugging this in for x. So we're plugging this in for the x. So we have a 3 times a 3y minus a 10 plus 2y is equal to 3. Multiply that through. We have a 9y minus a 30 plus a 2y equals 3. Add some of this up. We end up with a 11y. Move the 30 over to the other side, and we have a 33. So y is going to be equal to a 3. All right? What's x going to be equal to? Well, let's plug the y in. And we'll go to the second equation again. So we have an x is equal to 3y, which the y we know is 3, minus 10. So x is going to be equal to 3 times 3, which is 9. 9 minus 10 is a negative 1. So our ordered pair is going to be a negative 1, 3. And there we go. Again, checking. 3 times a negative 1 would be a negative 3. Plus, we'll just write that, negative 3. Plus a 2 times y, which is a 3. So 2 times 3 is 6. So plus 6. Negative 3 plus 6 is indeed 3. So we know that one's right. The lower one, we have an x, which is a negative 1, equals 3 times y, which is going to be a 9 minus 10. 9 minus 10 is negative 1. That one checks. That one checks. We're good. All right. On to the next one. Let's try it. So, again, we'll use the bottom equation. We're substituting this in for the y. And we have a negative x minus 2 times our y, which is the quantity, negative 3x plus 8, is equal to 4. Now it's just simplifying. So we have negative x plus 6x minus 16 equals 4. Combine, we have 5x. Move the 16 over. We have a 20. We have an x is equal to a 4. Okay? And then moving on, looking at the y, we have the let's see. We'll take the let's do it differently, and we'll take the top equation this time. So plugging in the x for the top equation, we're going to have a negative 4 minus 2y is equal to a 4. And that's going to give us a negative 4. I'm just getting rid of the parentheses here. And then we can move the 4 over to the other side, and we're going to get a negative 2y on the left, and plus 4 is going to be an 8 on the right. We can divide both sides by negative 2, and we're going to end up with y is equal to a negative 4. So, ordered pair is 4, negative 4. A quick mental check here. We'd have negative 4 minus 2 times a y. Oh, I'm sorry. Yeah, negative 4. Negative 2 times a negative 4 is going to give us a positive 8. And negative 4 and positive 8 is going to give us a positive 4, which matches, so check. And then in the bottom, we have a negative 4 is equal to a negative 3 times a 4 plus 8. Negative 3 times 4 is a negative 12. Negative 12 plus 8 is indeed a negative 4, so check. It works out. All right? Very good. Let's try just one more because this is maybe the only one that might try to confuse you a little bit. So try this one on your own first, and then we'll do it together. All right, so let's break it down. What are we going to do? Well, this one's set up so that x is equal to something, so we'll replace this top equation with the something, which in this case is just the y. So we're replacing the x's with y's. And we end up with 2y. I'll put it in parentheses just to stress that that's where we're substituting. 2y plus 3y is equal to 5. So now 2y plus 3y is going to be a 5y is equal to 5. Divide both sides by 5 and we end up with y is equal to 1. Here it's definitely easiest to go to our second equation, plug in y is equal to 1 for all the y's, and we end up with x is equal to y, which is 1, so x is equal to 1 as well. So the ordered pair here is 1, 1. Okay? So it was almost too simple, to the point where it might even throw you off. The x is equal to y. The x's and y's, they're the same value. They have to be the same value. That's why they both ended up being 1, because they're equal to each other. And then if you were to go back and check, you would say, well, 2 times 1 is 2, plus 3 times 1 is 3, so 2 plus 3 is 5. That does check. And 1, of course, equals 1. So they definitely check out. That would be our solution. All right? Very good. So this is where we will stop today. Hopefully that all makes sense to you. We did lots of examples today. And it's really nothing too complicated. But it is using some of the concepts that we've learned in the past in regard to equation solving and values, or like values. Or I should say equivalent values. All right, well, we will stop there, and I will see you again tomorrow.